In this lecture, we'll be composing prepositional phrases into nominal expressions. And we'll be doing so in a way that's more of a discovery method. And that way we can practice employing methodologies that we use to determine what certain morphemes mean when we encounter them. So in the case that we'll be doing, we have this phrase, the cat on the table, simple nominal expression. And we want to especially figure out what the meaning of on is. Now, we don't want to know in a very vague sense, like what is the notion of onness, but what we want is a formal definition of onness that we can compose and that we can incorporate into our semantics. So remember, the first step that we want to do is the syntax. So we want to have a sense of what this phrase means, and we'll be employing the DP hypothesis. Right. So D goes to NP, and then the prepositional phrase on the table adjoins to the NP. So we have NP going down to N, the cat These noun phrases have no other modification besides this prepositional phrase. So our structure is going to look like this, and this is the structure we'll be able to build our semantics with. So how do we do that now that we have our tree? Well, we start at the bottom. We know what table means, so we can incorporate it using the terminal nodes rule. So we put terminal nodes in the type. And make sure you put the terminal nodes in the type. Of course, nobody in the literature does this, because you should know, but as learners it's really helpful for you to keep track of what you're doing. Right? There are only a few compositional rules, and so it's good to know which one you're using. And there are only a handful of types that we've used so far, and the types will really help us make sure that we're putting things together properly. And then this will be the same at the non-branching nodes. This will be the meaning of the NP. And then we have the, which is terminal nodes type ETE. And it will take a function of type ET and give you the unique thing in the context that has that meaning, that the function applies to. And of course, we're leaving out the equals 1 bit. Now, these will combine to form something of type E. We'll skip the intermediate step, and we'll go straight to the last one for now. The table of X. And that employs functional application, and it's of type E. So far, so good. We have our table, right? The table. Now we want to add on. But that's the mystery, right? We don't know what the meaning of on is. And we don't know what its type is. Okay. So we'll leave it like that and move on. Now, given the syntax, we know that this will combine with the noun phrase cat. And we know what cat means. The result of this is going to combine with the. And we have the again. So again, terminal nodes, it'll be of type ETE. As far as we know in English, we have one the, although there is reason to suspect otherwise, as we saw. But this is going to be the same. We're not going to change that for now. Whatever cat on the table is, it's going to need to combine with the. And release a function of something of type E, right? And we can suspect that as a hypothesis. If it's right, then our intuitive notions of what this thing is ought to be important. So in doing so, what we're doing is bringing together the three key aspects of our analytical method. The first one is just the truth conditions, or the intuitive meanings. What kind of thing is a cat on the table, right? It is an entity, the particular cat. If I say, pick up the cat on the table, you'll go and pick up a particular object, right? So we have that. We also have the semantic types. And the types, remember, they will classify these semantic expressions in various formal ways. And they will be very useful because they help us constrain what can go together. Another thing that will help constrain what goes together is the phrase structure. And that's why we start with the syntax. Okay, maybe that's not exactly why. We start with the syntax because that feeds the semantics. But we can employ that fact in order to help us determine what goes together. So we know that this is the structure we need to figure out. And given these types, assuming they're right so far, right? Given these types, we can fill in the blanks and figure out what the types of these missing nodes can be. And thus formulate a hypothesis about what kinds of expressions they are. So, we have on. What is on? We have cat. And it's going to combine with on the table. What is on the table? Well, it's a modifier. And it can combine, it adjoins with cat in the syntax. And we've seen that adjectives adjoin with the cat in the syntax. And adjunction is recursive. So whatever this combination method is, it's got to be recursive. And it's got to express it in a way that doesn't saturate cat. And doesn't really saturate on the table either. And on the table can be thought of as a property that things have. If it's on the table, we can say it is on the table and it's true. If it is not on the table, if we say it's on the table, it's false. So we take a thing and we say it's on the table, that's true or false. Well, what we've got is a property of individuals. We have a thing and we get a truth value in return. So that suggests, going just by the meanings, that this is of type ET. Going by the types, we can suggest that it's also of type ET. Because if this is of type ETE, then its input, that is to say its sister, should be of type ET. Right? In theory, you could construct something of type ETE, but we're not exactly sure what kind of expression that would be yet. And we haven't seen that kind of thing. So if you thought about it, good for you, but if not, don't worry about it. Now, if this is of type ET, and this is of type ET, then this is either built by functional application, and this is of type ETET, or this is built by predicate modification, and it's of type ET. Now, things of type ET are properties of individuals. Give it an individual, it gives you a truth value. Well, that's just what we've said about on, right? Or, sorry, on the table, the whole constituent. We've said that you give it a truth, you give it an object, and it will tell you whether or not it's on the table. All right, so we plug it in. If it's a property, it should be of type ET. If it combines by predicate modification, then it should also be of type ET. And we think that it should combine by predicate modification because, just like adjectives, it's recursive, it doesn't saturate, and the type of the noun phrase is the same type as its output. So this is not a function, right? We're not taking the noun as a function. So all signs point to this being of type ET. And we came about it from two different directions. Right? Through the types and then through the meanings. And the phrase structure told us what we had to put together. Now we can try to figure out what this means as a property of things, but we can go further down too, to on. Right, what is on? Well, first, if we want to figure out what it means, we want to figure out what its types are, if at all possible. Because that will help us figure out what its formal meaning is going to be. Well, now we can figure out its type. It combines with something of type E, and it gives you something of type ET. So we can get something like this. Now we can't do functional application in the other way because this is not a function. So this is the only way these will get built. Now, we have an interesting issue. This is of type EET. We've actually seen that type before. We've seen it before. You think about where did we see it? We saw it with transitive verbs. So a verb like see or hit is of type EET. You give it an x and a y, and it's 1 if y hit x. X and y, 1 if and only if y saw x, and so forth. Well, on looks like it works the same way. You give it an x and a y, and it gives you 1 if and only if y is on x. Well, in that case, well, we figured out what it means. And then we can determine what it actually means to be on, right? Because you think on the table is one thing, but on the ceiling is another, or on the wall. Right? So a lot of different things that on can point to, and we could try to come up with a generalization for those, and that would be an interesting semantic exercise, but we're going to save that for another time, because here we're focused on the compositional meaning. And the compositional meaning looks like this. So how do we turn this type and this notion of give it x and y and it gives you this meaning into something we can express? Now we could go through the function notation route. Right? So f maps from e to et and so forth, so forth. And we're going to go straight to the lambda account though. So the way we do it, right, we can just read the types from left to right. So the first is type E. So we want lambda variable of type E dot. And that dot will match with the comma. Then we want something of type ET. But something of type ET is really something that takes something of type E and gives you something of type T. Right? We've curried the function. So we want lambda y in D sub E dot, and then comma here. Now we have something of type T. And what is that something of type T? Well, truth value 1 or 0. 1 if y is on x, 0 otherwise. And just like with transitive verbs, we can abbreviate that. We can abbreviate it on x, y. And there you have it. That's the meaning of on. The meaning of on, lambda x in d sub e, lambda y in d sub e on x of y, and that will be plugged in to here, using the terminal nodes rule. Right. So we've defined on this way. We don't have to write it again up here. Now we can plug in our arguments. So lambda x in d sub e, lambda y in d sub e on xy. Right. So we can use functional application. And we'll write the whole thing out here. We're going to be completely explicit. And we're going to add to it the meaning of table, right? Because that's the argument. Now, if you're listening carefully, you might be like, wait a second, did he just say table? Yes. And that was a mistake, because I should have said the table. Table is a noun, it's not the argument of on. The argument of on is the DP, the table. And so semantically, the table is what we plug in. Something of type E. And we'll do the same method we always do. Replace the leftmost variable in the value condition. Everything else survives. Lambda y on table y. That is to say, the function that gets you the set of things that are on the table. Now we can combine this with cat using predicate modification. Now this is changed to x, of course, because the rule states that we take this variable and we plug it in for here. We replace this y with it. So this is the function x saturates it, and we get that. And then we take the. So we get the unique thing in our context. The unique thing in our context that is a cat and is on the table. And that is how we build meaning of the cat on the table. That's what we want. It is unique. It is the unique thing in the context with that meaning. We can tell, right? If there are several cats on the table, and I say go pick up the cat on the table, then it's not clear which cat you want. And if there's no cat on the table, then it's a bit confusing. What cat am I talking about? But in each way, we've used the truth conditions, the semantic types, and the phrase structure to figure out, zero in, and figure out what our missing word meant. And we can do that quite regularly and try to understand these bits and pieces. So this is where the composition really shows its power. Right? When we know part of the meaning, we can use it to figure out the parts we don't know.